Hi, welcome to the Unit 3.4 video notes on shapes of molecules and polarity. So let's go ahead and just begin. We know that covalent molecules can be soluble in water, meaning they can dissolve in water, or insoluble, meaning they cannot dissolve in water. And we can predict the solubility of covalent molecules based on whether they're polar or not. So polar molecules tend to be soluble in water, and nonpolar tend to be insoluble, do not dissolve. And that's because of something called the likes dissolves likes rules, which essentially means anything with similar polarities will dissolve one another. So let's talk about, well, what is a polar molecule anyway? A polar means opposite, and a polar molecule has a negative end and a positive end, or we can say a negative side and a positive side. And I actually think end is a little bit more descriptive, and you'll see why in a moment. So here we have a water molecule. Water is polar, and that's why it dissolves polar covalent molecules, because of likes dissolves likes. And the top of my water molecule with oxygen is slightly negative, and I use this sort of partial negative symbol. And it's not an actual negative anion. It just means that this side has a lot of electron density. A lot of electrons are around here. And we know electrons are negative, so if you have a lot of electron density around here, it's going to be the negative side. And this side is sort of lacking the electron density, so it's slightly positive. And I color-coded it partial negative in red and partial positive in this blue color. All right, so we can use these symbols, these lowercase deltas, for partial positive or negative. And another way we can show that a molecule is polar by using a dipole moment. Dipole moment is just an arrow that points to the negative end of the polar molecule. So water is a polar molecule. However, when we take something like CO2, it's nonpolar. Now you may be looking, well, I see some red and I see some blue. I see a negative part and a positive part. Well, this is still nonpolar, because in order for it to be polar, notice how the ends here are both negative. You need to have one of these ends positive and one negative. Okay, so you need a positive and negative end. Since both ends are negative, this is nonpolar. All right, so if you need more time to sort of copy down the notes, I'm going to just scooch it down, and you can pause the video and copy the notes. All right, let's talk about now how can you tell if something is polar or nonpolar. Well, there are two criteria. The first one is it must contain polar bonds. So what are polar bonds? Just like a polar molecule has a negative side and a positive side, a polar bond has a negative side and a positive side of the bond as well. And so how do we tell? It has to do with difference in electronegativity. So this goes back to our periodic trends. Remember we said that electronegativity is the ability of an atom to pull electrons to itself in a covalent molecule or covalent bond, which is where electronegativity really comes into play. So electronegativity increases as one goes across the period to the right and decreases as one goes down. So if you have an electronegative element like fluorine that's very electronegative, okay, attached to something that's not so electronegative like hydrogen, the fluorine atom is going to pull the electrons in that bond closer toward it. So again, once again, this side is going to have a lot of electron density, and it's going to be partially negative, and this side is going to be partially positive. So for a bond like this, or a diatomic molecule, you use the difference in electronegativity to see how polar is it. If they're the same atoms, like two hydrogen atoms, they're going to share those electrons, equally. So this is going to be nonpolar, okay, because they're going to share it equally. Okay. So what do we need to do? So to see if the molecule is a polar bond, what we're going to do is take the difference in electronegativities. And electronegativities have values that are measured, and depending on how they're measured, the values may be a little different, but they're usually about the same. So let's take, for example, we have a hydrogen-hydrogen bond. The electronegativity of a hydrogen atom is 2.2. So the difference in electronegativity of the atoms in this bond is 2.2 minus 2.2 is 0. And that falls under the nonpolar covalent category. So if your difference in electronegativity is between 0 and 0.3, make that a little bit more clear, 0.3, okay, then you have a nonpolar covalent bond or molecule. And I say molecule if you're dealing with diatomics, two atoms. Okay, so nonpolar covalent. Now, if we take something like HF, as we saw before, Hydrogen has a 2.2 electronegativity. Fluorine has a 4.2. When we subtract them, we get 2. So this would be considered polar covalent, which fits here. So for polar covalent, between 0.3 and up to 2, it's polar covalent. Now, what if you have something that's really extreme difference in electronegativity, like sodium and fluorine? So that's our metal and that's our nonmetal. Remember, that makes this ionic. Well, what makes it ionic? The fluorine is so much more electronegative than the sodium, it rips the electrons away. And the difference in electronegativity will help us to predict that as well. So if we subtract 4.2 minus 1, we get 3.2, which falls in the ionic category. So above 2.0 is ionic. All right, so if you need more time to copy down these notes, go ahead and do that at this moment. Okay. Now let's go ahead and move on. So I said that there were 2 criteria for a molecule to be polar. It must have polar bonds. But the second part is that the polar bonds must be arranged asymmetrically, meaning that they can't be arranged evenly around a molecule. And you cannot tell that from a Lewis dot structure because Lewis dot structures are 2-dimensional, they're flat. So if you take something like this, the Lewis dot structure of H2F2, you will see that, oh, I can draw a line of symmetry that sort of goes, splits in the middle, this way, splits in the middle here. So I have a line of symmetry that goes through that molecule, and so this molecule is symmetric, so hey, it's nonpolar. Wrong. This molecule is actually polar. So let's take a look at how can we tell the molecule is polar. We need to know the actual shape of the molecule in order to predict its polar. So if we look at a CH2F2 molecule, here's one here. The fluorine atoms are sort of coming out at an angle, and the angle here is 109, about 109.5, and the hydrogen are at a twisted angle. This shape is called tetrahedral, all right? And I drew the tetrahedral using this wedge and dash method. So if you look at a tetrahedral, it sort of looks like a tripod, all right? A tripod with something sticking out at the top. So here I have the tripod on the side, and then at the top here we have something sticking out of our tripod. Now, in the wedge and dash model, the wedge represents a bond that's sticking out at us. So this fluorine is coming out at us, and the dash is a fluorine that's going in to the plane of the paper. So it's going away from us. Now the hydrogens, if I lay this flat, they're in the plane of the paper. They're right on that plane, so they're going to be just drawn as regular lines, okay? So this is a way of drawing a tetrahedral. And in this method, in this mode, you can actually see that this is a polar molecule. And one way to sort of help with that is if you draw the bond dipoles here, they would point to the more electronegative atom. In this case, it would be the fluorine. Okay. You can see that there's a pull of the electron density towards the fluorine. So this side is our partial negative, and this side is our partial positive. And I forgot to mention that before, that this is one way to show that a bond is polar is to use a bond dipole. Let me go back for one quick second. So we have a dipole moment, and that's for the entire molecule. So moment molecule, okay, that's for the entire molecule. Just a regular arrow, and it points to the negative side. For a bond dipole, you have an arrow that has a plus at the end towards the least electronegative atom, and it points to the more electronegative atom. So this side will be of that bond will be partial negative, and this side will be partial positive. And so this arrow looks a little different because it has that plus sign. And that's what I've drawn here. I've drawn the bond dipoles for the carbon-fluorine bond. Okay, so now that we see that this molecule is polar, and we can tell, in order to do that, we need to know the shape of the molecule to see if the polar bonds are arranged asymmetrically. Well, then the next question is, well, how can we tell what the shape of a molecule is? Okay, so to get the shape of the molecule, we can predict it using valence shell electron pair repulsion theory. And by now you should have watched the video on valence shell electron pair repulsion theory, which essentially says that the electrons around a central or focal atom, right, they're in these spaces called electron domains, and that includes electrons in bonds or lone pairs. And those electron domains are going to repel each other because, electrons are negatives and likes repel, right? So they're going to sort of repel each other. And the repulsion is what causes the shape. So if you look here in this structure, for our Lewis dot structure, these bonds are are close because they're not occupying the full three-dimensional space that a molecule can occupy. And so that bond angles here would be 90. But by occupying the full space, they sort of spread out, giving us a bond angle of 109.5. So this is 109.5, which is further away than having a 90-degree angle. Okay, so how can we predict the shape using VSEPR? Well, first thing is we want to draw the Lewis dot structures. Okay, and here we have our Lewis dot structures for the molecules you saw in the previous notes. And now the second step is to count the number of electron domains around a central atom or a focus atom. So in some cases, like in a molecule like this, there's no central atom. So you have to pick an atom that you want to focus on and count the electron domains around it. And that will give you a local geometry. Okay, so electron domains, again, is the space occupied by electrons. They can be in bonds or lone pairs. Now, for bonds, if it's a single or double bond, doesn't matter. This is still the same space, so single, double, triple, they all count as one electron domain. Lone pairs count as one as well. So if we're looking at NH2F, to count the electron domains, we would say find our central atom and then circle the spaces occupied by bonds or lone pairs around it. And that would be 1, 2, 3, 4. So this molecule has 4 electron domains. And one of those electron domains is a lone pair. So let's take a look at this structure. This structure is called Trigonal Pyramidal. And here's a model of that. A trigonal pyramidal essentially is a tetrahedral. So like here we have our tetrahedral. Okay, it's essentially a tetrahedral, but with the top taken off of it and replaced by a lone pair electron. Now, if you were to consider the lone pair electron in your geometry or in your, if you're looking at the shape of the molecule, including the lone pair electron, you would have what's called an electron domain geometry. And in this case, because it has 4 electron domains, no matter how many lone pairs, it would still be tetrahedral. But most of the time, chemists ignore the lone pairs because we really want to focus on the atoms when we look at the shapes, since those are our solid pieces. And in that case, the molecular geometry or the shape of the molecule will be trigonal pyramidal. So the electron domain geometry here is still tetrahedral, but the shape of this molecule is trigonal pyramidal. And for the most part, this is the thing that's most important. All right, if we look at our second example, CH2O, again, I counted the electron domains around the central atom, which is carbon. 1, 2, 3. It's 3 with 0 lone pairs. And so in that case, we would say it's trigonal planar. So let's take a look at trigonal planar. Here, CH2O, as you can see, it's sort of, trigonal means triangle, so it has this triangle shape, just like how this has a triangle shape, trigonal pyramidal. But the difference is with a pyramidal, it sort of comes up like a pyramid, whereas trigonal planar is a flat. Planar means flat, so we have a flat structure here. And so this is the name of the shape. Now, notice when I drew it more like a T-type shape, but it's really this type of shape here. It's not a T. And the bond angles here are 120. The last one here, if we're focusing on one atom, let's say we focus on the carbon with all single bonds around it. 1, 2, 3, 4, electron domains, 0 lone pairs. That's again our tetrahedral shape. So if you were given a Lewis dot structure or a chemical formula and you drew the Lewis dot structure, the process is you count the number of electron domains, and then you can use this chart to sort of help you. So if you know how many electron domains it has and how many lone pairs, you can tell what type of shape it is. So for example, if we looked at this one, 4 electron domains, 1 lone pair. In our chart here would be 4 electron domains, 1 lone pair. That's trigonal pyramidal. That's the shape. All right, so that is it for this video. So if you need more time to copy it, you can copy it from the PDF, or you can pause the video now. And I hope you have a quality day.